The Asset Integrity Dashboard has been created to allow for an improved understanding of the data collected from the non-destructive FMCW radar sensor. This summary video presents the results from one of the monolithic samples in the Asset Integrity Dashboard. We then present the parallel work which we completed beyond the scope of Phase 1 to demonstrate the future potential of the FMCW radar and the expected next steps. The advantages offered to structural health monitoring practices for the renewables sector due to this inspection technique include a non-contact, standoff inspection method. The FMCW radar augments and complements current state-of-the-art sensing suites, which include visual and infrared cameras in defect detection strategies. Our sensor has been proven to detect internal defects which are attributed to the surface and subsurface properties of a wind turbine blade. These include the detection of operationally induced material failures and manufacturing defects. The inspection method can be mounted in conjunction with camera systems on board a UAV and also coupled with advanced digital analysis methods such as machine learning and digital twinning systems. The Asset Integrity Dashboard was designed for wind farm operators to gain an operational overview. We have applied our Asset Integrity Dashboard tool to display one of the detected defects resulting from our evaluation of the capabilities from the wind turbine structural samples. We present the results from a monolithic sample which presented a defect of an adhesive joint thickness variation along the chord. The Asset Integrity Dashboard currently displays a 3D model of the monolithic sample alongside the real-world sample. As we pan around the real and modelled objects, we can identify the varying thickness along the chord, which is what we aim to detect using the non-contact and non-destructive evaluation tool provided by the FMCW radar. The Asset Integrity Dashboard has a number of buttons down the left hand side providing a user interface to access images of the real sample. This can be viewed alongside the sample parameters which display information of the adhesive thickness used within the structure. To ensure a full understanding of the defect type, a schematic highlights the main components of the sample, including the flange structure, monolithic material, and the varying adhesive thickness which is highlighted red. For this investigation, the sample was divided into square grids where the radar was aimed at each area to provide an understanding of the signal response to the material. For the presentation of these results, we utilised the data collected at 50 cm from the target interface. The experimental setup button presents an image of the procedure where we can identify the portable FMCW radar electronics and horn antenna, which is lightweight, low-powered and portable for deployment as a payload on a drone for non-contact inspection. The FMCW radar has been deployed previously on a drone as pictured for the defect detection of corrosion precursors. By clicking on each row on the 3D model, the data collected at 50 cm is presented graphically alongside the return signal amplitude from the reference sample. The user can then select the Overlay All Graphs button where the relevant graph is presented with the data overlaid. There is also the option to overlay the reference signal onto this graph. To identify the variation in thickness, we have also included a toggle depth map button to visualise the variation in thickness from the front view of the sample. We are developing the depth map function which is displayed as an example in our Asset Integrity Dashboard. The data can be represented this way as part of future work depending on the type of the fault. A conclusion button presents the findings from the investigation. The results demonstrate that at 50 cm, an excellent response correlation occurs within the monolithic sample, which demonstrates a varying thickness in adhesive, which was the objective. Grid 2, 6, 10, 14 and 18 have a thicker adhesive layer compared to grid 3, 7, 11, 15 and 19. Therefore, due to the thicker adhesive, an increase in return signal amplitude was detected. This infers a consistent signal response to adhesive variations where an increase in thickness correlates to an increased return signal amplitude and a decrease in thickness correlates to a decrease in return signal amplitude. Next, we highlight the parallel work which was completed beyond the scope of Phase 1 of this project to demonstrate the future potential and value created from the FMCW radar. This presents the expected next steps. We utilise a robotic manipulator arm to provide an automated scanning process. This dynamic method was used in conjunction with machine learning techniques. The utilisation of machine learning models on FMCW radar return signals collected from the different turbine blade samples demonstrate that we can classify blade types by composition and diameter differentials of 3 mm with 98.5% classification accuracy. The result also shows the capability of this novel approach, as when trained with compressed or limited range of radar signal classification, the accuracy still achieves over 92.9%. This highlights the suitability of FMCW radar and data-driven approaches to act as a robust discriminator for a more accurate and deeper defect detection within compromised asset structures. A significant amount of value is created for offshore inspections due to FMCW radar sensing. This includes surface and subsurface detection of faults, a non-contact lightweight sensing method which can be deployed as a payload on a UAV, along with several deployment scenarios for asset integrity inspection, including inspection of surface metals for corrosion, and subsurface detection of wind turbine blades and civil infrastructure. We thank you for your time and look forward to any future collaborations.